Welcome to Calculus 1. In this lecture, we will be going over part 2 of an overview of basic mathematical concepts. Let's begin with statements, questions, and sets. Statements can have true or false values. For example, 1 plus 2 is equal to 6 minus 3 is a true statement, whereas 3 is greater than 5 is a false statement. Now what about x plus 3 is equal to 7x minus 1? This has no true or false values, rather it's a question. The question is, can you find a value of x such that this is a true statement? Now let's consider x is less than 4. What values of x make this inequality a true statement? Well, in this case, we have the open interval negative infinity to 4. All these values of x will satisfy this inequality and make it a true statement. So inequalities involving x specify a set of real numbers. Now let's introduce two theorems. Let's start with the basic arithmetic theorem. The basic arithmetic theorem states that given true statements, you can add, subtract, multiply, or divide both sides by the same factor, whether it's a positive or negative number, and get another true statement. However, for inequalities with a negative factor, and for multiplication and division only, you have to reverse the sign of the inequality. For example, 3 plus 5 is equal to 1 plus 7 is a true statement. We can add 10 to both sides of this equation and get another true statement. Here's another example. 3 is less than 6 is a true statement. We can multiply both sides by negative 1 and get another true statement as long as we reverse the sign of the inequality. Now let's introduce the basic algebraic theorem. Given a sentence, you can add, subtract, multiply, or divide both sides by the same factor, whether it's a positive or negative number, and get another sentence. You have to be careful though, because the factor may depend on a variable. And for inequalities with a negative factor and for multiplication and division only, you have to reverse the sign of the inequality. For example, consider this sentence. 12 plus x is equal to 3x. We can divide both sides by negative 4 and get another sentence. Another example is 3x is less than 6. We can multiply both sides by negative 1, flip the sign of the inequality, and get another inequality. Now let's talk about specifying sets with inequalities. So for example, take x squared minus x minus 6 is greater than 0. What x is specified by this inequality? Well, we can factor this into x plus 2 times x minus 3 is greater than 0. We can then find the zeros of this inequality. That is, what values of x will make the left side of this inequality equal to 0? Well, here we have x is equal to negative 2 and x is equal to 3 will make the left side of this inequality equal to 0. So we need to find values of x such that x plus 2 times x minus 3 is greater than 0. So to go about this, we can make a table. We can test values of x that are less than negative 2. We can test values of x that are between negative 2 and 3, and we can test values of x that are greater than 3. And we need to find whether these values will make the whole thing positive or negative. So for example, when x is less than negative 2, x plus 2 will be negative. When x is between negative 2 and 3, x plus 2 will be positive, and when x is greater than 3, x plus 2 will be positive. When x is less than negative 2, x minus 3 will be negative. When x is between negative 2 and 3, x minus 3 will be negative. And when x is greater than 3, x minus 3 will be positive. So we can multiply the symbols in the column and get that x plus 2 times x minus 3 will be positive when x is less than negative 2, negative when x is between negative 2 and 3, and positive when x is greater than 3. So if we plot it on a number line, we can see that this inequality will be satisfied when x is less than negative 2 but not negative 2, and as well when x is greater than 3 but not 3. Now let's talk about an example with absolute values. What x is specified by this equation? The absolute value of x plus 5 is equal to 10. Well, we can break the absolute value into both its positive case and its negative case. So in the first case, when x plus 5 is positive, x plus 5 is equal to 10, which gives that x is equal to 5. In the second case, when x plus 5 is negative, we have negative x plus 5 is equal to 10, which gives x is equal to negative 15. So x can be 5 or negative 15, and both those values of x will satisfy that equation. Now let's talk about specifying intervals with absolute values. Consider the following. The absolute value of 3 minus 2x is less than 10. What x is specified by this inequality? Well, we can break the inequality into its two cases. The first case is when 3 minus 2x is positive. When 3 minus 2x is positive, then 3 minus 2x is less than 10, which gives x is greater than negative 7 over 2. In the second case, where 3 minus 2x is negative, we have negative 3 minus 2x is less than 10, which gives x is less than 13 over 2. So if we plot it on a number line, it looks like this. It's an open interval from negative 7 over 2 all the way to 13 over 2. Now there's another way we can deal with the absolute value. Remember, we have the absolute value of 3 minus 2x is less than 10. We can simply put negative 10 on the left side of the inequality, which will get rid of the absolute values. Try to convince yourself that this is true. All you need to do is break the absolute value into its two cases and then apply the transitivity axiom. We can then subtract by 3 throughout the inequality and divide by negative 2. Here we get the same result as we got in the previous example. Negative 7 over 2 is less than x, which is less than 13 over 2. In general, when we have something like the following, the absolute value of x minus c is less than delta, we can put negative delta on the left side of the inequality and get rid of the absolute value. Here, c and delta are simply just real numbers. Now let me give a precursor to the definition of limit. Consider the absolute value of x minus c is less than delta. Recall that the absolute value of x minus c can be interpreted as the distance between x and c on the real number line. So here, what we're really saying is the distance between x and c is less than some number delta. So it looks something like this, where we have an open interval centered around some number c. Here, x can be any value from c minus delta all the way to c plus delta, and those numbers will satisfy the inequality. Again, try to look at this and convince yourself that this is true. Now consider this. 0 is less than the absolute value of x minus c is less than delta. Here what we're saying is that x cannot be equal to c, because if x is equal to c, then the absolute value of x minus c will be 0. But here we're specifying that the absolute value of x minus c must be greater than 0. So it will look something like this, where there's a hole at c, and x can be any number between c and c plus delta, as well as any number between c and c minus delta. Again, try to look at this and convince yourself that this is true.